Hi, I'm Priyanka Sumitra. Today I'm going to be talking about singular value decomposition. So singular value decomposition is a form of matrix factorization. So let's take a matrix A. It's in the reals. It's an n by n matrix. So m rows, n columns. As I only have 5 minutes, this is a very high level, hopefully intuitive explanation of what singular value decomposition is. As it applies to every matrix, it's a very commonly used form of matrix factorization. And so let's say we have a matrix, it's a large image, or it's in a common machine learning use case, number of samples by number of features. So many use cases for singular value decomposition, Fourier transforms, list goes on. So let's get more into what singular value decomposition is, why it applies for every matrix, and how it could possibly be used for rank reduction and other algorithms. All right, so again, I'm only dealing with the reals, similar intuition to for the complex case. Now we know A, like I just said, is this way of storing data, but let's think of it as a linear transformation. So what do I mean by that, right? So really what a linear transformation is more limited. What a matrix can really only do is rotate vectors, scale vectors. By scale, I also mean reflect, multiply by a negative value. And it can project vectors. So that's these three things is having a matrix having this limited scope of operations is really what singular value decomposition is trying to take advantage of. So now let's look at that in the context of singular value decomposition. What is singular value decomposition in specific doing? So U here, U and V are both called orthogonal matrices. And what that basically means is that they're doing rotations. So U and V, so U is an m by n matrix, V is an n by n matrix. And so U is basically performing the rotation it does in the m-dimensional space, so for the column vectors. Then it goes into sigma. And what is sigma doing? Sigma is basically doing the scaling. So sigma looks like m-dimensional vector or matrix for m rank of n. Sigma m, it has zeros all over here, and it's basically scaling each of these vectors. And immediately you can see how this is used for rank reduction because given my vectors u1, u2, dot, 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 and vectors v1, but you can see how these zeros, we don't need to encode the last few values of each of these matrices, as it's already considered to be zero. And anyway, so because those are zeros, sigma is basically projecting these vectors in U onto this n-dimensional space, and it's scaling them respectively. And now I'm rotating them again in this n-dimensional space, which is where V comes in. So rotate, scale plus project, and rotate. And so you'll see what that basically means is U transpose is equal to I, and U transpose U is equal to I. These are properties of our orthogonal matrix, and that basically means that they're rotating. Sigma is basically a diagonal matrix, which is what gives it the property that it's scaling. And then because it has the extra zeros and it's transforming it to the n, which makes it transform it to the n-dimensional case, it can have zeros to the side as well, depending on the dimensions. It's scaling it, it's projecting it onto my n-dimensional space. And And yeah, so you can see how if I order it such that sigma 1 is less than or equal, each of these sigmas, each of the values entries in my matrix sigma are called singular values. And if I order them such that the first value, sigma 1, dot, 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 is less than or equal to sigma 2, dot, 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 I can have it such that you can see how the values that are scaled less are less important to the transformation. So I can also be doing rank reduction. Anyway, so I hope this gave you a good overview of what singular value decomposition is. Thank you for listening.